Hey there guys, welcome to Unit 9, Notes A. In Unit 9, we're going to study thermodynamics, and in Notes A, we're going to look at heat specifically and compare it to temperature. So thermodynamics or thermochemistry is the study of energy, and thermodynamics actually looks at how the energy will change through a system. We're going to focus on the chemistry side of thermodynamics, where we're looking at changes that occur during a physical or chemical change. The energy in particular that we're interested in is heat energy, hence thermo in the name. So in the first part, we're going to look at heat versus temperature. So say it's a cold day out and you want to stay warm. We have fire A, a little bonfire on the beach, or fire B, a much bigger bonfire. Which one will keep you warmer? Probably the bigger bonfire. But which one would have a higher temperature? Well, you may know that you can actually tell the temperature of a flame from its color. For example, the blue flame of the Bunsen burner would be a much hotter flame, whereas the orange flame that we see here would be a cooler flame. And since both flames are the same color, we can see that they're burning at about the same temperature, or average kinetic energy. But because bonfire B has much more fuel and is much larger in size, has more mass being burnt, it's going to emit more heat. So heat is more of a total energy emitted, whereas the temperature is the average kinetic energy of the particles inside. So heat versus temperature, they're not the same thing, and they have completely different units to compare them. Heat is a type of energy, and so the units that we're going to use are mostly joules. You may have also heard of an energy unit called calories, so we'll look at the conversion between those two as well. This heat energy is some type of thermal energy typically transferred by conduction or contact, convection or circular motion through like a liquid, or radiation, pure energy waves that can even travel in a vacuum. So these are all different ways that heat could be transferred. How do we know how hot something is? Well, typically we translate that into temperature. Temperature is measured in, for example, degrees Celsius or degrees Fahrenheit, and even Kelvin. When we look at temperature, we're looking at an average of the kinetic energy of the particles. So this is going to tell us roughly how hot something is if we were to touch it. Something to note here, which is going to be a much bigger deal in some of our future notes, you can actually add heat to a system without changing the temperature. What you would be causing then would be a phase change. Think law of conservation of energy. The energy can either go into changing the temperature or changing the intermolecular forces, or stored energy. All right, so what is thermochemistry? Our study of energy as it relates to physical or chemical changes. We're going to look at how much energy something absorbs or something releases as it goes through, for example, a phase change or as a chemical reaction occurs. The thing about heat is that it always flows from hot to cold. Some people think that if you touch something cold, you become cold because the cold then is transferred to you. It actually doesn't work that way. Cold is just the total absence of heat energy. So if something feels cold to you, that is because it is absorbing your heat. If you touch something and it feels hot, that's because it's giving heat energy to you. So the thing about heat flow is that it always flows from an area of high concentration of heat energy to low concentration of heat energy, or from hot to cold. So we have two important terms to describe this. If I'm looking at something that is endothermic, that thing would be absorbing energy. And if you touched it, it would absorb your energy, and so your hand would feel cold. We're going to look at a new variable for heat. The letter is Q here. That's going to refer to the heat energy. And whenever you have a positive Q, then you're going to be endothermic. You're going to be looking at a system that is absorbing energy. If Q is greater than 0, positive Q. An exothermic system would be releasing energy. And so if you touched it, your hand would feel hot because the energy is being transferred from the hot object to your hand. And so your hand would increase in energy and feeling warm. So the Q for an exothermic process would be negative, showing that it is releasing energy. The sooner you can get the signs down for the Q, the better. Positive Q is endothermic and a negative Q is exothermic. All right, so I mentioned that we would look at the units of calories and joules. So here's the conversion factor in red right here, along with some other conversion factors that may be helpful in some of your other problems. This is a big one though. 1 calorie is equal to 4.184 joules. 1 calorie to 4.184 joules. So that's going to be able to be used as a conversion factor if we're given calories and asked for joules or vice versa. We could use this for dimensional analysis. Something else I want to note is you may have heard of calories just in the idea of a nutrition label. For example, if you pick up a candy bar, it'll tell you how many calories are in that candy bar when you look at the nutrition labels, things that look like this. Well, the nutritional calories are actually equal to 1,000 chemistry calories. 1,000 lowercase c calories, or a kilocalorie, would be equal to 1 nutritional calorie. So when you look at the energy labels in the United States, it's a capital C. If you look at some energy labels in some other countries, they may use kilocalorie, for example here, kilocalorie, all representing 1,000 calories. But they don't actually write it as thousands of calories on that candy bar. That might make you think twice about buying that candy bar, right? But you should know that there is a similarity. 1 nutritional calorie is actually 1,000 calories. So it gives you an idea of how much energy you're intaking when you eat the candy bar. All right. Let's move on to a formula. This is going to allow us to calculate the amount of heat in an object. So, or in a system. We've got Q, which would be the total amount of heat, not temperature, heat energy. And so the units are going to be the joules, magnitude of heat, total heat, which is going to be a function of M for mass, C, something called specific heat, which we're going to talk about in just a moment. It's kind of like a constant, except for it depends on the substance. So each substance will have its own specific heat. And then we're going to look at the change in temperature. And this time the sign for the temperature is of the utmost importance because it's going to dictate whether Q becomes positive or negative, which in turn is going to tell us whether it's exothermic or endothermic. So we really want to make sure that we're getting the right sign for delta T. So whenever you find delta, it's always final minus initial. So we're going to take the final temperature, the temperature at the end of the reaction, for example, minus the initial temperature, or the temperature of the system before the reaction started. When we find the difference there, we'll get our delta T, and that is going to dictate the sign for Q, because M and C are always positive. All right, so let's look at specific heat, this value of C. The variable C that was just in the last formula stands for specific heat. So specific heat is the amount of energy it takes to raise 1 gram of a substance by 1 degree Celsius. So say you have a gram of water and it's currently at 32 degrees Celsius. If we wanted it to become 33 degrees Celsius, we would need to add 1 calorie or 4.184 joules of energy. That is going to then allow the 1 gram of water to increase 1 degree Celsius. So the same thing with all these different substances. If I had 1 gram of carbon dioxide, I would need to add 0.843 joules in order to get 1 gram of carbon dioxide to increase 1 degree Celsius. So every substance has a different specific heat. The higher the specific heat, the more energy you would have to put into a gram of substance in order to change its temperature by 1 degree. That basically means that the lower the specific heat, the easier it is to change the temperature. Think about some of these things like copper and iron with very low specific heats. If I have a very low specific heat, it's going to change temperature very readily. I only have to put 0.382 joules into a gram of copper to change its temperature by 1 degree Celsius, but I have to put way more than that, 4 joules of energy into a gram of water to get that same temperature change. So the lower the specific heat, the more the temperature will actually fluctuate. The higher the specific heat, the less the temperature will fluctuate. Think about us being warm-blooded. Our bodies are made of mostly water, which is great because water is good at resisting changes in temperature. And we don't want the temperature of our bodies to be wildly fluctuating. And that is all helped by water having this really large specific heat. So now that we kind of have an understanding of what specific heat is and what the difference between temperature and heat is, let's try a problem. So the first thing I'm going to do is write my formula. Q equals mc delta T. So that can guide us a little bit as we go through the formula and identify our variables. So how much heat? So heat is the variable Q. And when I don't know how much, if it's saying what's the heat or how much is the heat, that's my unknown. So I've got my Q question mark. Now I've got 50 grams. So would grams represent mass, specific heat, or temperature? Grams is the unit for mass. So my M is equal to 50.0 grams. The next numbers it gives me are the 80 and the 50 degrees Celsius. This really should say 80 degrees Celsius also. So I have two temperatures. One is 80 degrees Celsius and one is 50 degrees Celsius. Oops, let me not mess up my sig figs here. 50.0 degrees Celsius. And so what is the difference here? Which one's the initial and which one's the final? Because we want to make sure we put them in the right order when we solve for delta T. So the system says it cools from 80, meaning it's starting at 80. So that would be my initial temperature. And it goes down to 50. So that would be my final temperature. So when I solve for delta T, I want to do T final minus T initial. So the final is the 50 degrees Celsius. And the initial is the 80 degrees Celsius. Delta T. So then my delta T is actually a negative 30.0 degrees Celsius. As far as significant figures go, when you subtract, you go by decimal places. And so I'm going to keep that 0.0 for my delta T. And then having the larger number after the subtraction sign makes my delta T negative. And we've got to think, does that make sense? Did we decrease the temperature? Well, yeah, we went from 80 down to 50. So that does make sense for our delta T. I have Q unknown, and I still haven't found C anywhere. So the question now is, where can I find my C? Because I can't have two unknowns and solve the problem. The C is going to have to be looked up based on the substance. What is the specific heat for copper? And that's going to be on a reference table. So I'm going to pop back to my last slide, see if I can read through here. Copper's specific heat is 0.382 joules per gram degrees Celsius. So pulling that from the list on the prior slide, now I have C, delta T, and M. So now I can plug these things into Q equals MC delta T. I'm going to make a little bit of room here. So Q equals the mass, which was the 50 grams, the specific heat, which was 0.382, a number we looked up based on the substance being copper, and then the delta T, which we found to be negative 30.0 degrees Celsius. So this is just straight multiplication. Three numbers to multiply together. When one of them is negative, my answer will be negative. So Q is going to equal a negative number. And let's look at the units. Grams cancels with grams, and degrees Celsius cancels with degrees Celsius, leaving my unit to be joules. So now I just need to multiply the numbers together to figure out what Q is losing in joules. There we go. So Q turns out to be negative 573 joules. This negative sign is very important. When you write Q, you have to say whether it's positive or negative. And for thermodynamics, I usually write the positive sign because it's positive on purpose. In this case, it's negative on purpose. Negative 573 joules to show that heat is given off. And that makes sense because it's talking about cooling and it's dropping the temperature. So you can usually tell from the words if you're going to have the right sign, and you want to make sure that you end up with that correct sign. Something else I wanted to point out on the PowerPoint's version of doing this, they've kind of used a system of equations where I solved for the delta T first and then just plugged that number in. You can also just plug that into parentheses here as well. Just doing the parentheses first is going to give you that times these two numbers. So of course, either way works. Basic algebra. All right, let's look at another example. Iron has a specific heat. They wouldn't have to give it to you in the problem, but they did. knowing the substance, you would be able to look up the specific heat, or C, which is 0.446 joules per gram degrees Celsius. Actually, something I should mention about looking up the specific heat, be careful of your units. The ones that we're going to be doing are usually in joules per gram degrees Celsius, and that's the reference table that I have posted. But if you are Googling other specific heats, be careful because sometimes they do use different units here, maybe calories, maybe per Kelvin, things like that you'll see online. All right, back to the question. Next number is my grams. So grams is going to measure my mass, so 7.55 grams. And then it's going to absorb 10.33 joules of heat. So heat, or joules, we're going to use the letter Q. Whenever you're writing the Q, you give it a sign on purpose. The word absorbs would indicate that that system is absorbing or bringing in endothermically absorbing heat. And the sign for that is positive. So see how we have to know our signs for the Q? If it's endothermic, it's positive. So it's absorbing 10.33 joules. If it said releases, you would want to make this a negative sign. Now we're looking for what is the change in temperature. So that means I'm solving for delta T. That is my question mark. And then the next sentence, it actually gives me one temperature and asks for the other. So let's take this one step at a time though. First, Q equals MC delta T, always writing down the formula. Then I'm going to plug in the Q, the positive 10.33 joules. And then I'm going to plug in the mass of 7.55 grams. And even the C of 0.446 joules per gram degrees Celsius. And I'm solving for delta T. So to isolate delta T, I'm going to be dividing the 10.33 by each of those numbers. My grams already cancels out. And then when I divide joule by another joule, that will cancel out, leaving Celsius in the denominator of the denominator, which we know is really in the numerator. So I've got degrees Celsius as my unit for temperature. So now I just need to actually do this division. What is 10.33 divided by each of these numbers to get the delta T? So let's go ahead and see what we get math-wise in the calculator for our delta T. Okay, so when you divide to isolate delta T, we get a change of 3.07 degrees Celsius, which is the answer to our first question. Now we still have one more question to answer. What is the temperature change, what is the final temperature based on that temperature change? So this is essentially using the delta T formula. Delta T equals T final minus T initial. And the delta T, we can plug in on the left to be 3.07 degrees Celsius. The final temperature, or the initial temperature, is what we're looking for. Let me rephrase that. Which one are we looking for? The final temperature or the initial temperature? We've got what is the final temperature. So that means I have TF as a question mark. And then it says originally, which is a hint that this is the TI, the 22.0 degrees Celsius. So then I'm going to keep TF as the variable, my unknown, and set this up as minus 22.0 degrees Celsius. So the question is, what minus 22 degrees Celsius gives you the 3.07 degrees Celsius? So basically, we're going to add 22 to both sides. So we can isolate TF. And we get a final temperature of 25.1 degrees Celsius. So when we increased from 22 by 3.07, we get the 25.1 degrees Celsius. So now we've answered both of our questions. What is the delta T, our 3.07, and what is our final temperature, the 25.1? All right, guys, that's going to wrap up Notes A for Unit 9. The next set of notes, Notes B, is all about calorimetry. We're going to continue to use this Q equals MC delta T formula, and we're going to learn how to use that to find temperature changes when situations are a little more difficult. It's a really cool experiment called calorimetry. We'll see you there.